the topic. I did manage to draw this fabulous artwork before my wrist gave out on me. This picture represents everything we're going to be talking about. We're going to talk about in the next 3 to 4 lectures, which is the interfaces. Specifically, not just the cathode as I mentioned here, but potentially also anode, so treat it as the electrode. And then when we talk about interfaces, when we were talking about liquid systems, we were talking more about, how does the liquid electrolyte affect the SEI growth. That's basically been the interface, the dynamic interface and interphase phases that have been of interest. When we move to solid systems, which, that's where the technology is going, we are interested in the electrode-electrolyte interface and interphases that form. But more often now, we have to also consider the coated particles. So that's going to be the interface and the interphases that we have to care about as well. And so that's what we're going to be talking about today. So here it goes. Let's see how long I last before I have to dance with my hands. Okay, so in terms of interfaces, we have the cathode, and we're going to be talking about cathode particles because that's the reality, right? It's not one monolithic thing. It's typically the technology now is that you're mixing cathode particles, whether it's micron size or nanometers or whatever, coated or uncoated. We're going to be talking about particles. So here we'll treat them as spherical particles. So a lot of the studies that we'll talk about have been on just bare particles. If you have cathodes, and then if you have bare particles, then these bare particles interact with the electrolyte. Okay. And here we're talking about solid state electrolyte. And the myth that there is no interphases that form in between cathode and solid state electrolytes has sort of gone out the door these days. So that's something we care about in terms of trying to understand the chemical species that are at these interfaces. More often now, there are a lot of developing technologies around coated particles to protect the bare particles from chemical decomposition, as well as electrochemical decomposition. So when I talk about chemical decomposition, I mean when you put these materials together, they're dissimilar, so there's going to be a chemical reaction right at the interface. Even before you start cycling, they're just at rest. The fact that they're dissimilar chemicals, the dissimilar materials, means there's going to be a chemical potential difference, and thus there's going to be an induced decomposition right at these interfaces. And sometimes they evolve quite dynamically, sometimes they don't, depending on the decomposed products. So these coated particles also interact with the solid state electrolyte. If you're making a composite, they're also going to interact with the conductive carbon, so that's an interface that we have to care about. And then also the current collector. This is something that we haven't really talked about as much, but now when we're putting these particles and making these composites, especially if we're going to be talking, well, not just the cathode, but depending on the geometry of the current collector, there could be interactions with that as well. So all these three, I should say 1, 2, 3. Oops. Whoop. Let's try to see. All right. 1, 2, 3. This also 1, 2, 3. So you can see quite a number of interactions already here. For stabilizing cells that can operate and achieve high capacities, we also have anodes, and typically they're lithium metal, but more often now we also need to talk about lithium metal alloys, so that you're not just working with bare lithium, but let's say for all intents and purposes, lithium metal is going to represent just like the metal anode or metal alloy anode. That also interacts with the electrolyte. So that's an interface that we need to care about. And then there are more interfaces that we need to understand within the solid state electrolyte itself. Right. The electrolyte particles will also interact with other electrolyte particles. And often we care about the grain boundaries. We care about the voids that occur also at these between these particles within the electrolyte. So already you could see there's a lot for us to consider. There can also be grain boundaries within the cathode itself, and maybe some voids, but we'll focus on more so the grain boundaries and potentially cracks within the particles, especially when you start cycling your cell. These cracks can form over time. So you can see, there's quite a number of interfaces that we need to keep track of. So that's what we're going to talk about. Now, in terms of the solid state electrolyte, I'll focus on the more, I will say mature, because there has been quite a bit of research already, in the last 10, 15 years on oxides, halides, and also sulfides. So here, when we talk about decomposition, chemical decomposition at the interface, right? We want to go back and understand, what is the driving force for the decomposition, and it comes down to the thermodynamics, but also kinetics if you're, going to nanostructure these materials. Right. So we go back to our discussion of thermodynamics and how we're going to detect possibly the chemical species that are formed, but also how we can interpret the electrochemical measurements as an indicator of the decomposition at these interfaces. So here, if we plot chemical potential, so this is increasing chemical potential going up. We have our anode. Let's say we pin that at some level. Cathode. Okay. So that's what we have so far. Depending on how the material lines up, let's say this is the energy low, the chemical potential, the lowest unoccupied molecular orbital of, let's say, an oxide versus the highest molecular occupied molecular orbital. So you can see here the chemical potential differences, will also cause some either an SEI that forms or a cathode electrolyte interface that forms. Okay. Now, there's been quite a bit of discussion of more, let's say, agiridites and other halide-based electrolytes. So how do those line up? Well, they're pretty similar. This could be, depending on which halide, I should say. This is a generalized case, but it could be a little bit higher than the oxide as well. So let's say these are halides. And what we'll talk about a lot are the sulfides, but those have a much smaller window. So here you can have smaller SEI. So the chemical potential difference between, halides, oxides, sulfides, and that of where the chemical potentials for anode and cathodes are quite different. So you could see what we've talked about in terms of utilizing the sulfide-based solid electrolytes, and for the reasons that they have high ion conductivity. But this whole module is going to be about how do we stabilize the interfaces so that we maintain the high ion conductivity, because typically what will happen is decomposition at the interfaces will cause the production of binary compounds that are not as that don't have high ion conductivity, and in fact sometimes they block ion migration, which defeats the purpose of making an all solid cell. So clearly there is a mismatch of chemical potential of dissimilar materials. And so this will lead to chemical decomposition as well as, once you start cycling, of course, electrochemical decomposition. Okay. Okay. So, well, what exactly forms? I've been mentioning these binary compounds, and it's all driven by the redox of either the metal centers or the oxides, the anions themselves. So you can have evolution of oxygen and say. So in terms of decomposition, what we're going to look for are, so we'll talk about possible chemical species that form at these interfaces. So decomposition products. Because before you go in to characterize these interfaces, you have to know what to look for, right? So in terms of oxides, I start with them first because they've been quite popular. There's been quite a bit of research, and I'm going to focus on some of the more well-studied compounds. Not that these are the only compounds out there in terms of solid electrolytes, and also coating. So I say solid electrolytes, but there's been a lot of studies where the solid electrolytes are not just used as the separator layer, but also mixed in with the cathode to make a cathode composite. That's been a popular strategy for decreasing impedance. So let's say specifically, looking up. Whoop. All right. So in terms of the reduced species, here we focus. Here we focus on the titanium product. So here, titanium could go from a 4+ state to a 3+ state. So titanium being a 4s2 3d2 electronic configuration element, in the oxide state, it tends to be a +4 state, so that it gets back to a nice closed shell system. It can be changed to titanium 3+ with some holes for charge balance. And so typically you don't find titanium 3+, but just as a thermodynamically equilibrium product, like you wouldn't normally find Ti2O3, but you would find the more thermodynamically energetically favorable product, which is TiO2. But at these interfaces where you can have stabilized, these species can be stabilized due to higher energies at the interfaces or voids and what have you. You can have all these metastable species, and so you can encounter titanium 3. And in fact, at the nanoscale, if you try to produce titanium dioxide, TiO2, you will produce that. But at a certain size, you can actually, as in you go small enough down to 10 nanometers and such, there are certain facets that will stabilize titanium 3+, and in fact, titanium dioxide, the titania shows up more as like a bluish color as opposed to, you know, the white that you often expect of titanium dioxide, okay? Well, and then there's also LLZO, the stuff garnet that we talked about. Right. So here, LLZO has been, as we've discussed, you know, quite attractive of a solid electrolyte because it can be stabilized against lithium metal, mostly. I mean, the stability window for LLZO goes all the way down to almost 0 volts versus lithium plus. It's more like 0.05, so you can get pretty close. So the SEI that forms, that chemical potential difference, is not going to be quite as much. So in the reduced form, the species that you can expect could be LI2O, right? That's not high ionic conducting compound, lanthanum, and also if you go low enough, potentially zirconium metal. Now that is rare, but it is possible. And in terms of the oxidized species, if you go outside of the electrochemical stability window, you can form other species like lanthanum, zirconate. You could also form more lanthanum oxide, and there is potential to evolve some. I mean, if you drive the system to not equilibrium enough, you can start just breaking the material. Okay, and then there's also LATP. So what's been studied is substoichiometric. Okay. So here, the electrochemical window is a little bit smaller, but you also can form titanium 4 going to titanium 3. Okay. So then we can think about the decomposition products of the gyridites and other halides. So typically we'll talk about the chlorides, but it can be any halide really. So that's noted as X. Okay. So here the electrochemical window is rather small. So outside of 1.7 volts versus lithium plus, or greater than 2.3 volts versus lithium plus, you can have reduction down to species such as lithium phosphide, Li2S, and also lithium chloride. Okay, so Li2S is quite insulating. Li3P is more electronically conductive, but these are low in terms of ionic conductivity. In terms of oxidative species, you could oxidize the P2S5. You could also form just sulfur, right? If you push the system far out of equilibrium enough, or stability enough. Now, we can also, let's talk about other halides that have been investigated for their high ionic conductivity. So outside of the voltage window of 0.6 to 4.2 volts versus lithium plus. Now this window has gotten wider, which is really attractive. You can have reduced species that are, well, they're pretty similar, right? Lithium chloride, yttrium, or the oxidation. Oxidized states of, well, if you charge balance, you could form these products. Now, what is the issue with evolving Cl2? I see a disappointed look from the other side of the room, which indicates what we all know, right, is that this is a highly toxic and extremely dangerous chemical weapon, basically, as has been historically been used in the past. Okay, so it's not ideal, right? So there are plenty of advantages of this solid-state electrolyte, but these are some of the concerns that we have to deal with. And in terms of sulfides, let's talk about our favorite sulfide solid electrolyte, LGPS. So you could have what are some guesses? Sorry?
2 volts versus lithium?
Yep. So 2 volts. Oh, you mean you mean the oxidized state, or that's below? Are you talking about the lower end or the higher end?
Something around 2 volts. I'm not sure which side.
Well, I can tell you it's very low.
Okay.
If we were to round to the nearest integer, you would be correct regardless of what you had answered. The electrochemical stability window is really small. So in terms of the reduction, the species that can form under reduction, what are the guesses for this quaternary compound? Sorry, I can't hear. Okay. Stoichiometry? 5p6. Oh, so just lithium phosphide.
Oh, no, P and an S.
Oh, okay. Well, if your answer is, could it ever happen in the universe? The answer is yes. Could it happen thermodynamically? In the bulk, this species would not form typically in the bulk, but just because someone hasn't proven that you can't find it, right? Your answer is valid. That's the nuanced answer response to your suggestion. The more direct response would be no. Okay, but yes, in terms of, but it was a good attempt. Yes, so we'll say, oops, sorry, I meant to write Z. So typical species could be, right, so these species could form. But in terms of binaries, you could also find lithium phosphide that's thermodynamically stable. You could also form Li2S. You could also form our favorite Li15G4, so we haven't discussed germanium, but in the context of silicon, 15:4 is a common ratio in terms of the bulk from the bulk phase diagram. In terms of the oxidized species, the species that can form are P2S5, sulfur, and also something that's stable, germanium sulfide as well. So you can see already from this list that these are the species we have to contend with when you start cycling. And these are the species that are going to either aid or be detrimental to the cycling of your cell. Okay, so now it's not always that decomposed products are detrimental. And in fact, and especially if they create vacancies and from voids, or they create vacancies from the fact that your decomposed products need holes for charge balancing to come up with a neutral state. And in fact, there have been studies where increases in the number of vacancies due to the decomposition have increased ionic conductivity, have decreased impedance, but there have also been cases where the increase of vacancies will decrease the performance. And it all has to do with the material that you take. So either you go with, let's say, LLZO or LATP. It's not obvious that, if you create more vacancies, you're creating more void space, and thus you decrease performance of the cell. That's absolutely not true. It's solely based on the chemistry of your cell, and it's not a hard, fast rule that voids and vacancies are always detrimental. Okay, so so then if we now if we try to rank the voltage window, in terms of voltage stability window versus lithium plus, if we have, let's say, 4, 3, 2, 1, and 0, here we have pretty high. This goes all the way down to, see if we have lithium, the halides, then you have maybe 3, all the way down to as close as 0, almost, but not really, LLZO. We talked about the iridites. They're a little bit smaller, around 2. The sulfides, specifically LGPS. There's also been discussion of, I haven't discussed LiPon, right? But that's been looked at in terms of polymer, more amorphous solid electrolyte. And so when you look at this and you say, okay, if the electrochemical stability window is limited for some, but they have high ionic conductivity, and then larger for others, but they have lower ionic conductivity, the strategy could be just to mix and match. Okay. So you could do this at the interface and basically create a buffer layer. You could also mix and match in terms of either coating the cathode. So you could try to, let's say, if you have cathode particles that are oxide based, let's say NMC or NCA, and you know when you put it right directly next to a sulfide based on an electrolyte, there's going to be induced decomposition. You can try to buffer that a little bit. So you could take your cathode particle, create an interface with, let's say, another oxide. So this could be some oxide base material, and then you have sulfide based solid state electrolyte, all mixed in. Okay? And this could be your composite in terms of designing a stable cathode composite that minimizes electrochemical decomposition as well as chemical decomposition. Okay? And so that basically has been the solution, is to either coat with, phosphate or oxide-based compounds around the cathode particle to minimize these decomposition. And while these, lithium phosphate is not high does not have high ionic conductivity, but it will allow lithium ion migration. So it's lithium ion permeable while protecting the cathode particle from decomposing. Okay, so these are the popular choices, and they've been proven to work very well with oxide oxide nanoparticle. Oxide cathodes. Okay, let's see. Do I have 10? Okay. I said NCA. These are examples. We'll also talk about later sulfide-based cathodes, but unfortunately, I have to cap it here for today so that I can run. So our discussion is a little bit short. And in fact, I'm already running late. But we'll pick up here next time talking about kinetic control in terms of nanostructuring and what happens at the nanoscale, right at the interface. And we'll also talk about the space charge layer that occurs between these particles, between the cathode particles as in the solid state electrolyte. Because once you have these voids, you have depletion zones in terms of lithium ion concentration that will affect the ion conductivity. It will also affect the impedance, and in fact, it typically drives up the impedance, making your cell less cyclable and just,